This is Thibault. We came from OpenDS, and today we'll talk about the Cryptolocker. Did I just hear someone saying fucking Cryptolocker again? So we'll introduce a very nice technique called ripple effect, and we'll try to give you a live demo experience with really cool visuals. A little bit about myself. So I'm Ping. I'm Chinese. I came to the U.S. for school. Went to University of Arizona. Go Wildcats. So I had my research in data mining and machine learning, and of course InfoSec. If you may be wondering why I'm not on the other side of the cyber wall, well, maybe one day, yes. So here you go.
All right, hackers. My name is Thibault. I work for OpenDNS. I'm in the research team. My research is on visualization. I'm Parisian. I moved to California 3 years ago. And I really wanted to introduce myself. I really want to answer that question. Security and visualization. This is the question I get all the time. You remember that's old school kind of demo scene where you would download a crack and you see a small animation on the cracks you've been downloading. Well, I fell in love with that a couple of years ago, and I was like, I need to learn how to do those things. So I did reversing for many, many years. And I learned OpenGL techniques and 3D techniques. And that's how I moved to the US because I got an internship at NVIDIA. And then I found this awesome opportunity in the research team where they were really interested in visualization, especially knowledge-based visualization. We'll talk a little bit more about that a little later. So yeah, that's my story. All right, let's get started.
Yeah, this presentation is going to be an interesting format. So both Thibault and I will be talking at the same time. So we'll be doing a little bit dancing at the stage. So we'll go through a quick introduction of what OpenDNS is and what data we have. And then this is the awesome house developed security graph. It is our kind of proud child. That is the knowledge base of the whole cloud-based security solution. Then we'll talk about this ripple effect technique, and we'll use this Cryptolocker as a live example. Then we'll talk about a little bit how bad this thing has been, what impact it has done. Then we'll go to the conclusion. So whenever I start speaking, I'll talk about data, and of course, the first thing, the size of the data. So the scale of problem we are facing at OpenDNS is 60 billion daily DNS requests coming from 200 countries. That is 17 plus data centers across the globe. And we have active 50 million users who are sending all their DNS requests to us. So our job is, the fun part is how to make sense of this huge amount of data and how to make security analytics not just efficient but also fun. This is a web view of all the information we'll be indexing related to millions of domains on the internet. And we have a bunch of DNS-related network features, attributes. As you can see, IP addresses, ASN, TTL, etc. And we have a dozen of predictive models analytics from the backend system that gives us all kinds of security indicators that range from temporal analysis, fast flux classifier, and the client geodiversity anomaly detection type of techniques. And by the way, this interface is open for security community. So if you want to have access, just talk to us, and we'll give you this gold mine of information. So, well, when we look at those data, how do we, get to the conclusion whether this domain or this network entity is bad or good? We have tons of analytical models here, and sometimes you can visually see some like obvious pattern. For example, the traffic volume. For this website, you obviously see a huge spike of traffic within like 24 hours, and it just comes and went away. You also see like two sections there. They are called the co-occurrences and the related domains. So what are they? Well, no, obviously those are some like not good-looking legit domains right there. Those are all like DGA-looking things. DGAs are dynamically generated algorithm. That is most of the time, like the malware use DGA generated domains as command and control server. That way, they can just use and discard, so they can defeat this blacklisting kind of defense technique. We'll talk about how we find out those co-occurrence domain and also related domains in a little bit while. So here's just some, kind of boring, flat data format of the thing. Now we're gonna give you some, more interesting representation of this data.
Absolutely. But before we do that, I'd like to cover a couple of fundamentals so we're all on the same page. I want to talk a little bit about knowledge. So let's step back a little bit. We basically have, on one hand, a lot of periodic jobs that are creating knowledge every day. So a couple numbers, 35 million names per day, 62 million related domains per day, and 21,000 spiking domains per day. So we'll come back to that later. But basically, we have scripts, jobs that create a lot of data. And the security graph, what is a security graph? It's a graph, right? So it's set of nodes and edges. And more particularly, it's a semantic graph applied to DNS problematic. It's really interesting for us because it helps us to explore the internet as we know it. Think of it as a Wikipedia of what we know of the internet. Of course, we use indicators, as you've seen, has been described, to perform amazing machine learning. But the point here, why we're so interested to look at this in terms of graph, because we can analyze the ontology. The ontology is the model of the model. So all the scripts create knowledge, relationships, nodes, edges. And if we can find the structure and the way this data is actually built, then we can do pattern detection, even if it's stochastic pattern detection, right? If there's a pattern in this structure, then we can predict it, we can anticipate the threats. So we're going to do a small demo so have a better feel of what I'm talking about here. So same thing, we're going to look at Cryptolocker.com. And I'm going to just let you enjoy the animation. Whoa. Let you enjoy the animation, and then I'm going to talk a little bit about it. I can speed up the process a little bit. All right, so what are we looking at here? The first view, I apologize for the quality of the screen. So the first view was basically showing only a flat view of a domain, like IP, ASNs. We have a couple of different pages. What it does here is like we take a domain and we explore the neighborhood in terms of co-occurrences, related domains. So here we're showing only two types of edges, right? This is, S-graph, edge type. Here we go. So we have different type of edges. We have edges connecting domains. We have edges connecting IPs, different types of nodes. Here's the ASIN number. Here's an IP address. Here's the domain. We can navigate through it and basically explore everything around Cryptolocker.com. So this is like a 3D view of the previous flat view that you've seen, and we gather them all together to see basically to appreciate the complexity of the data that has been created by our periodic jobs. All right, let's go back to our presentation. So what did you just see? You saw a 3D engine, right? It's running OpenGL, where nodes are 3D vertex, edges are lines, and every security graph attribute is interpreted as a color, size, width, activity. You haven't seen activity yet, but we're going to come back to this later. And the animation at the beginning that you've seen, like the expanding phase, is basically called the force-directed algorithm. It's super simple. It's inspired by electrical forces models. Basically, if two nodes are connected, they attract each other. If they're not, then they repulse each other. So you end up having something that has a molecular structure and that expands in space once you actually start running the physics engine. The main reason we want to use something like this is because it's a dynamic and auto-adapting layout. We can remove nodes, we can add nodes like over time, and the layout just adapts itself. Whoops. And of course, you've seen a couple of Python scripts highlighting the features of the model. So we're going to come back to that later as well. The main question I want to answer is why? Why do we want to use visualization to do this? First of all, first reason is the shape. It's kind of a philosophical explanation, but we have algorithms that populate the knowledge graph. This creation, we made those models. This creation, we understand it really well. But the output is complex because the input are clients, right? They're actual humans, and it's hard to understand their behaviors. So we need something, we need a layout to look at something we have no idea what shape it has, right? We need a layout that is defined by the model structure, and this is why we use this. It's closer to, I would say, the natural shape of the data, right? Because you treat information as matter. And of course, we take advantage of the GPU to do that. We have a really performant GPUs, and we can entangle the information in 3D space just using that. Of course, as I said, security graph is dynamic. It's changing every day. We have, a lot of different modifications, node added, deleted, a lot of different things, and it helps us monitor the evolution of this security graph over time because of this dynamic layout. And of course, investigation-wise, humans are so much better at processing shapes than numbers. So it's so much easier to look at something that has colors, shapes, nice textures, whatever, to understand what's going on, this complex structure that we've created. It's a solid tool to build hypotheses and heuristics. The next models that we're going to build, next generation models, are completely going to be based on this. And the next point, which is I'm super excited about this, is it's a semantic-based threat detection. It's threat detection based on something that has semantic value, like Wikipedia, for example. And if you take the analogy of this knowledge, the security graph being like a brain, a thought in the brain, if you look at EEGs, is has a shape, has different neurons active together, connected together. So what we want is basically do exactly the same thing. We want to detect this pattern inside our brain and apply actions to it. Those actions would be threat containment, blocking some DNS domains, things like that. And the next point, why we want to do this, if we're able to grab one part of the security graph and apply threat detection on it, then we can parallelize it. We can decentralize the pattern detection, which is amazing. All right, I'm going to show you a visual example of how we can use the 3D engine to explore things we don't know about the internet or in the security, using the security graph from a couple of domain we already knew. All right, so you're looking at domain IP graph. The domains are yellow, yeah, kind of yellow. The IPs are purple. So it's a graph of spiking domains. So it's like basically a domain IP mapping, right? So how did we create it? This data set. No, it's the mapping, IP domains mapping.
IPs corresponding with domains.
Yes, yes. So we started with a couple of domains we're interested in. They were spiking domains, right? One that has a lot of traffic coming, and we weren't expecting it. So they are the white dots that you see here. So what we did is basically, we take those domains, we look at their IPs they map to, and then we take the other domains that are mapped to the same IPs. So in terms of graph, it's like a BFS focusing on the IP domain link with a depth of 2, right? So this is what we're discovering, the neighborhood of those domains, IP and domain-wise. So what do we already know about those domains? What you see here, like the red color represent what we already block, and green color is what we whitelisted, and the white color is we don't know anything about it. But what we see, like starting from those seeds, we see that there's like a bubble, a sphere that we don't know anything about. So we can basically run a classifiers on it and see that half of it is detected as malicious. Red means malicious in this case. So it's like a way to focus our investigation on parts of the graph from malicious domains that we already know. So this technique can be used, and it's exactly something very similar that we've used with Cryptolocker. And I'm gonna let, so yeah, this is the zoom of the investigation area that we have. So some of them, it doesn't mean all of them are malicious, but it's like basically a way to filter all the domains that we have in the security graph to detect domains that we don't know anything about yet. So I'm gonna let Ping introduce the ripple effect, which is very similar and applied to Cryptolocker.
Right, so back to some dry stuff. Well, this is just a name, like ripple effect, we call it this way. Actually, it is a really simple and generic process, like we apply day in and day out for any case investigation. Think about it. Every case investigation starts with, a little bit information and you got it like from somewhere, like from the community, someone told you about. Then how we can finish the process by, getting all the undetected and explore the whole unknown space. So this is about, ripping out from the seeding intelligence and get the newer and the unknown. So what can be a better example as Cryptolocker? This thing started early September. Then hundreds or hundreds of people, kind of like have to deal with this nasty stuff. So any one of you have ever dealt with this? Like Cryptolocker, I'll get into it just in a little bit. So this is a computer attack. So the threat has been, reported so extensively. And what it does. So you get infected with Cryptolocker, or it is a malware threat, right? Normally with email attachment, so it comes in as a lure. Like you got this new job offer, or here is this is detail of your concert coming up tonight. Then when you get infected, then Cryptolocker, sit on your computer, and what it does, it goes to contact its command and control server and try to get a encryption key. And then after it gets the encryption key, it will index all your data files, not just on your local hard disk and also like remote network drafts. Then it encrypts all your data. So all your data becomes, I don't know, something you wouldn't understand. So you lose access to all your data, and the only way to get out is to pay the ransom, which is normally $100 to $300 or 2 Bitcoins, as most currently. After you pay the ransom, then I've heard like those attackers has been honest. They will give you the decryption and decrypt your data files. Tens of thousands of users has been affected with this, and after 2 months, people are still crying about it. What the attacker has done, they are obviously pretty good crypto experts. They practice really good crypto techniques. So once your data is encrypted, there's no way you can decrypt them yourself. But we noticed like a critical step is to get the key before they can encrypt your file. So we think, okay, what about we just stop them right from there, not letting them get the key? This is one of the Cryptolocker sample running in a VM. It is trying to contact a bunch of like control servers to get the key, but we blocked it. So it has no way out. So it just keep rotating the whole DGA name list and try to contact any of them without success. So what we see here, it is a whole sequence of DJ-looking name lookups in the system. But it's not practical that we grab every copy of Cryptolocker sample and run them in VM and generate all the names. And if we already have the sample, that means we're already infected. Someone has already fallen victim. So blocking wouldn't be, the most effective way to stop them. So we want to predict all the names. We want to block them before anyone gets infected. Well, it would be easy if we know the DJ algorithm that will be used in the malware. But the thing is, it's not that easy to decrypt the file, the malware binary, and get the DJ algorithm. And the DJ algorithm wasn't known until first week of October. That is like a month after people have seen the Cryptolocker thing. Okay, so here comes a nice thing about co-occurrence. This is one of the predictive model we'll be using in our system. And what it is, I want to use a example has been known for years by Amazon recommendation system. That is the beer and diaper example. So everyone has heard about them. That is like people find out when people go pick up a diaper in the grocery store, they often also pick up a pack of beers. And we call that as co-occurrence. That is a strong kind of correlation and association between two items. And in our data, we have indexed, billions of records. That's billions of DNS lookups from all the DNS users to all the domains like on the internet. Then each of the DNS lookup stream kind of give us the sequence of all the names one client has been looking up. And what we notice is when Cryptolocker is in action, it looks up a bunch of domains, right? And they are all being looked up like within a really short time window. This pattern spread across multiple users. So we can kind of generalize from this lookup sequence thing and find the co-occurrence pattern between different names. Question?
But a DGA that uses other factors like time or IP address
Yeah.
will have box co-occurrence. You have to reverse engineer the DGA algorithm to try to get all the names.
Well, say you have one computer, right? Then a SDGA use your computer features like the timestamp and etc. It generates a bunch of names, right? It generates like 1,000. And the good thing is when we know one of the names here, then it's pretty easy by looking at this co-occurrence thing to find the other 999. So that's the idea here. So we cannot do this like without knowing anything. Yeah, they'll change, and the next day we kind of like keep seeing this whole sequence of things being looked up, and they all following like similar patterns, right? We're also looking at the name stream patterns. This gives us a time locality of these lookups, and it was generalized across like millions of users. This is just for the eyes who really like reading pseudocode. It's pretty simple. It's just recursive loop. Once you discover some domains, and you keep discovering more by looking at the same pattern. Okay, now I'm done with the dry stuff. Fun time begins again. We cannot collaborate with some other parties try to take down them, but it's not the easiest thing to do.
Okay. So Pinga just introduced the co-occurrence concept. So if you look at it in a visual way, so what does it look like to do the ripple effect? So I'm going to show you a screen capture of one of our web application. Same, it's OpenGL, it's the same engine, just running in the web. So what we do, we start from a Cryptolocker domain that we know. We request all the co-occurrences, and you can see that all of them are like new DGAs. And then we take the neighbors, again, one more time, co-occurrences, and we repeat that process as much as we need. So of course, it's really boring to do it manually, so we made a script to do that. And what I'm going to show you right now is basically the result of such a script that basically digs inside the security graph on the co-occurrences relationship. So here we go. I'm going to load a data set of Cryptolocker co-occurrences level 4. Same thing. We're going to expand it in 3D space like this, just because it looks cool. As graph type. So the same node types, right? Because we're looking at only domains, a graph between domains linked by co-occurrences. So what I'm going to show you right now is basically a score of every node in this graph. So we call that the infected score. It's basically same thing. It's basically red means we block the domain, green means it's whitelisted, and white means we don't know much about it. Okay. So as we can see, so you're looking at the co-occurrences graph. As we can see, there are a lot of domains that we extracted from the same seed. Seed is here, right? I'm gonna use the mouse, probably simpler. See, so that's the first domain we use to actually do the extraction. And then we basically requested the neighbors of the neighbors, etc., etc., etc. That's how we build the script. So it has 4 levels of traversal. Where's my script? Yep, there we go. Okay, so let's go back to the infected thing. So we can see that a lot of them have been detected as DGAs. And what's really interesting is to see the clusters of malicious domains. If you take the analogy of the security graph being a brain, then it's pretty much like looking at a tumor and trying to isolate it to just block everything we don't want to provide to our customers. So another thing that is really interesting is that we can see that some of them are obviously like good-looking domains, right? And it's still connected to some malicious ones. And to do that, we have basically a confidence score for each co-occurrence edge. This score helps us to basically put a threshold on how much we want to dig in the co-occurrence that is not so sure. So yeah, it's basically just like biology or like being a surgeon. You just look at the internet and basically you try to extract as much malicious domain as you can. So this is a view of basically the neighborhood of a Cryptolocker domain on 4 levels.
What's the green stuff? Can we look at that?
Absolutely. So they're the ones we're basically whitelisted.
So why is there a reference to them?
Because sometimes in our logs, we have malicious domains that are connected to good ones, right? And this is where the confidence score comes in, because it doesn't happen that much. So we can see that the score is like much smaller. Actually, let me just show you. Let me reload that again. I want to show you. It's probably going to be more explicit. Here we go.
You never explained what a connection means.
Oh, she did. Yeah, the co-occurrences is like on.
So a connection between a good domain and a non-malicious.
I'm going to that. Yeah, I'm going to answer your question.
There's a lookup.
Mhm.
There's somewhere from a client.
Yep, I'm going to go into that. So I hope this is going to answer your question. So basically what you're looking here, there's like new particles. Okay, let me just color the nodes again according to their infected score so we can see clearly. Okay, so I've added here like a couple of particles floating on the edges, right? So the speed of those particles is basically the confidence score of the co-occurrence edges. So if you look in this like Cryptolocker neighborhood, you can see that there's some activity. And like if you look at the places where we have a good cluster connected to a bad one, we can see that the particles are like, oops, sorry. We can see that the particles is much slower than the places where it's like an obvious Cryptolocker neighborhood. Okay, here. Does that make sense to you? Does that answer your question?
Well, kind of. But so does that mean that the IP address that showed Cryptolocker behavior also did a DNS lookup of that believed to be good domain?
Yep.
So it might be, for example, a natting gateway, and some other machine that was not infected did the lookup,
Yeah.
or a corporate gateway, or some other unrelated traffic, or traffic prior to the infection, or what?
Yeah, absolutely. Yeah. So the co-occurrence thing is now, just absolutely has to be Cryptolocker domain. It co-occur with Google.com or Facebook.com. So, but we can clearly see the Cryptolocker domains are pretty localized, right? All the other co-occurrences kind of isolated, and we use like different heuristics to remove the noises. Yeah. The co-occurrence has a time window component. Say it is like 60 seconds. Yeah. Then you see the particle speed. That is the confidence thing. That's the frequency and the density. So it has a time window component as well.
For example, if Cryptolocker did a lookup every 60 seconds or every 5 minutes, then you could see from the pattern that it was a Cryptolocker.
That we didn't see that pattern. It's not like a strict, like a uniform interval between the lookups. Yeah. Okay, so this is a quick like 2 weeks study of the Cryptolocker footprints. It's just how bad this is and how well spread this attack has been. We're seeing the requesting pattern for each of the domains like only live for a day, and then for another day it is a new domain. And each day we're seeing from 10 million to 30 million requests to those Cryptolocker domains. So Cryptolocker is using 1,000 DGA domains every day. Yeah, so altogether it has been tens of thousands. Yeah. And all these Cryptolocker domains have been resolved into a set of IP addresses. Of course, we keep track of this infrastructure, and we have seen around 20 IP addresses has been used, like rotated day in and day out. So Cryptolocker has been rotating these domains on multiple days across multiple domains. Until today, most of them has been sinkholed. So only a few IP addresses still alive. And of course, when we get hold of these IP addresses, and we can map to more names has been used on Cryptolocker. I think late November, people have seen like Cryptolocker being delivered with Zeus, botnet, and other nasty stuff. So we've been seeing like a whole new set of like bad names associated with the domains, with these IP addresses. And of course, we have them all contained. So some like visual view of the infected clients.
Yeah, so in terms of the impact of Cryptolocker, it's nice to visually analyze it as well. So this is like a well-known geolocation visualization. So we can see that Cryptolocker has impacted a lot in the US, in Europe as well. The colors basically represent the continent code. So it's actually the UK, a small presence in Asia, Oceania, Africa, and South America as well. But there's another view I would like to present to you. So it's It's a little tricky to understand. So look at the top left one. So it's basically the whole IP space, right? So 0.0.0 is here, and 255.55 is here. So it just rotates, uses, so an IP address can be split into A point, B point, C point, D, and you basically use a geometrical level to put it on the arc shape. And then the color represents the continent code again. So Asia is yellow, light blue is Europe, dark blue is North America. There's Africa that we can barely see here. That is green. And then the white ones are the reserved IPs. So used for reserved for future use, or like just for local networks. I'm sure you all know about this. And the one on the right is basically a country view. It's the same thing except that the color represents the countries. So we can see that, for example, for the light blue area, it completely split into a lot of different countries because it's Europe, right? And Asia is the same. So North America is not a split. So if we do the same thing on the infected client IPs for Cryptolocker, we can basically make a visual to combine the geolocation of those IPs and the same as their IP numbers. So we can see that, for example, Cryptolocker has tracked a lot in North America and Europe. So we already know that, but also in the low IP space, there's much less data in the higher IP space. All right, reaching our conclusion.
Yeah. So today we talked about this co-occurrence technique and the way how we detect Cryptolocker and contain them, and we hope we will give you a kind of a live experience, like how we combine data, science, art, and design, to bring security analytics to a new whole experience. And now it is the living creature Cryptolocker domains, like in a kind of like worm shape here. And that's it. Any questions? Sure.
If you go down a bit, there's a separate cluster, an isolated cluster, it looks like.
Oh, it's not the same data set. This one is it's not the same data set. This one is purified.
Yeah.
But we can go back to the other one if you
No,
want.
this one is this is real data?
Yeah, it is.
So, but what does it mean that there are two clusters which are connected to each other and isolated from each other?
Yeah.
I mean, there's an independent Cryptolocker operation that has a separate DGA.
They are independent on different days. They are still the same Cryptolocker operation. Yeah, we took the data like across multiple time slices, across days, just to kind of give you a more spread out view.
Is this because the date is different in different parts of the world at the same time? It's tomorrow in Japan already, as an example. So the dates change, so it started with the new DGA?
You can say it that way, right? So it's the same DGA, but with different parameters. It gives you a different set of names. Yeah. So across multiple time zones or anything like that, it will be a whole new set of names.
Do you see something split off as the time zone sweeps across, as the new day sweeps across the continent?
Yeah.
So that would explain it.
Did you find any correlation with the domain name servers that are serving up these domains? Is there one relationship between the domain and the domain name servers, or if you look at the domain name servers and see that there's domain name servers?
Yeah, that's a very good point. We have a database for the name servers and all the names hosted on the name servers. So we've been also grabbing more names from the name server side.
Right, did you see, it seems like there'd be a lot fewer domain name servers than are domains, correct?
Yep.
And so could you like just see just the fact that the domain name being resolved to this single domain name server is simply declared bad?
Actually, no. Actually, the name servers have been seen like, hosting all kinds of stuff. So it's not like the single indicator that we can, confirm this is Cryptolocker. But you're right. Like we definitely monitor this like limited set of name servers. Yeah. easier to keep track of, but it's not the kind of like only indicator there.
But it looked like there were only a couple dozen hosting sites that were actually the destination sites. So
Yeah.
are the DNS servers the providers for those services, or do they have their own name servers that they're running?
We haven't seen their own name servers.
They're just using provider name servers with okay.
Yeah, go
Have
ahead.
you considered like reverse engineering the Cryptolocker server and feeding back an encryption key of like all zeros and just telling people, hey, try to unencrypt it with all zeros?
You mean like you know, kind of reach out to the servers and get the decryption key from those people?
Cryptolocker works by compromising a host and then reaching out to its SQL server and grabbing an encryption key to encrypt the disk.
It's unique for every client.
Yeah. It is like
Why not
unique.
just block it anyway?
So why not like try and create a server that keeps track of clients that are connected to it, and then feed back some encryption key for that client?
Yeah, well, that's possible, but that will require a lot of whole setup thing, like, you know, and you need to get to the other side of all the infected clients. A lot of clients on our network, they are not our customers. They're just using our DNS as a provider. So it will be a whole different story if we just reach out and get all the things set up for them.
Awesome. Thanks. Feel free to come talk to us if you have any more questions. Anything you want to talk about?
And when she's already served, I'll ask you to form a line heading in that direction of the dojo, because otherwise it will be a little difficult for people to move between rooms. There's a couple of sections. One of them is meat, and the other one is more vegetarian. So if you don't find what you like, just move on to the next section, and that's it. Thank you, guys.
Good.